In this lecture, we're going to talk about free energy in the context of equilibrium. And I hope that what we'll be able to show is that free energy is really the driving force for a reaction to go in the forward or the reverse direction in order to reach equilibrium. So let's take a situation where we are theoretically at equilibrium. We would say then that our free energy is zero. There's not going to be a driving force to go forward or reverse, and those rates of the reaction are going to be equal in the opposite and reverse direction. So we can relate free energy to equilibrium using this equation right here. And I'll talk about what each of these are here first. So we have our change in free energy is equal to our standard change in free energy. So this standard change in free energy is at 1 bar pressure. And if it's a solution, it's at 1 molar concentration. And so this change in free energy that our equation is equal to, this is just free energy not at these standard conditions. So it might be at a different pressure. It might be at a concentration of 0.05 instead of 1. It could be a lot of those kind of subtle changes that we see in everyday lab life. The R value here, this is our good old R that we've been using throughout the series. It's 8.314 joules per mole Kelvin. And our temperature will always be in units of Kelvin. And our Q value is really our reaction quotient. And this is calculated just like Q, and this is kind of how we decide what our ratio of products to reactants are to determine if our reaction is already at equilibrium, if it needs to proceed towards the reactants to reach equilibrium or proceed towards the products. So that's always going to be that concentration of our products over the concentration of our reactants. And we always have our superscripts are always going to be the coefficients for each of our different products or reactants. So we can see that the free energy for our non-standard, so realistic conditions, is going to be whatever we calculate for a standard free energy plus a modifying factor. And that modifying factor is really that reaction quotient and then our constant and also temperature adjustment. So if we are actually at equilibrium, then this really equals 0 right here. Our free energy at non-standard conditions is 0 if the system is at equilibrium, because it won't be proceeding anymore to the reverse or to the forward direction to reach it. So under those circumstances, when this equals 0, we can rearrange this equation a little bit, and we can get to this arrangement where our standard free energy is equal to the negative of R times our temperature and then the natural log of our equilibrium constant. And so this is the same as our reaction quotient. We're just saying now we're actually at equilibrium. So that reaction quotient equals our equilibrium constant. This itself can be rearranged as well. If we wanted to solve for our equilibrium constant using free energy or standard free energy, we could arrange it this way with x to the exponent with our negative of our standard free energy divided by RT. So these are the two forms that you can use this in. And we'll typically use this. So let's just walk through an example of it, kind of how we might use it. If we were studying a reaction, N2O4 in equilibrium with 2NO2, we might have the question, well, what is K? Does this favor reactants or does it favor products at equilibrium? Which K would help us with? And so to calculate K, we can use standard free energy to do that now, which is a powerful tool because these standard free energies of formation are typically just published tables. We have a lot of work has gone into generating these values and studying them. And so we have standard formation free energies for both our reactant and our product. So we can figure that out. So we're going to use two equations here. We're going to calculate the change in our standard free energy by calculating the sum of our free energy of formations for our products and subtracting from that the sum of, that's a terrible sum sign, the sum of our free energy of formations for our reactants times by their coefficient. So that can get us to our standard free energy, and then we can use that to actually calculate our K value, because that standard free energy then will be equal to negative RT natural log of K. And we can use the rearranged version where K is going to be equal to our exponent to the negative standard free energy divided by RT. So let's give this a try. All right, so I'm going to first calculate my free energy. I'm going to use the given values right here. So for my products, it's NO2, and I've got a coefficient of 2. So I'm going to have 2 times that NO2 value, which is the plus 51.3 kilojoules per mole, and subtract from that the standard free energy of formation for my reactant, which is that N2O4. And it has a coefficient of 1 in front of it, so I don't need to actually multiply it by anything meaningful. And it's plus 99.8 kilojoules per mole. All right, so that's how I set this up, and then it's a matter of plugging this into my calculator. I get plus 2.8 kilojoules. So now I can use that in my equation to calculate my equilibrium constant. So plugging that into our next equation, I know that, K is equal to the exponent of negative standard free energy divided by RT. So it'll be exponent to negative 2.8 kilojoules per mole, or sorry, just kilojoules. Yep. Divided by 8.314 joules per mole Kelvin, and times our temperature, which is 298 Kelvin for the reaction. So I'm going to highlight right here that we've got a problem with our units. Our value is always going to give those energy units in joules. And right now I have kilojoules for my my standard free energy. So I need to adjust that and convert into joules. So that's going to be our 2.8 kilojoules times 1,000 joules for every 1 kilojoule. Is going to give me 2.8 times 10 to the third joules. So I'm going to replace that value here with a value that has the units that'll cancel out with our R value. So 2.8 times 10 to the third. All right, so now plugging all of this into my calculator, I'm going to get a value that says K is equal to the exponent of about negative 1.13, which should give me 0.32. Remember, these are unitless values, and that definitely corresponds to a K value less than 1. It's pretty close to 1. It definitely falls in that region of equilibrium constants where we'll have a meaningful amount of both products and reactants together at equilibrium, but it will favor our reactants.